Okay, so let's start today's central exercise session. As usual, we have a chat where you can ask any questions that you want regarding this exercise sheet. We'll discuss sheet number 11 today. And your moderator on today's chat channel will be Arda. Would you please introduce yourself, Arda?
Hi, everyone. My name is Arda, and I will be moderating today's central exercise session.
Okay, great. Thank you. As usual, we have the chat channel available here on chat.tum.de, and please use this channel here, MA9714-CE, for your questions regarding the central exercise session. As I said, we'll be discussing sheet number 11 today, and before we start doing so, I would like to post a quick survey to see which problems you had with sheet 11. So basically, there's 3 types of problems on that sheet. That's either the integration over domains given in the form of some vertices. Then we have integration where you are using polar coordinates or some other type of coordinate system. And then we have volume computations, like, for example, H11.6 or H11.7.
Dr. Ritter?
Yeah.
So before we even start, we have one question about the exam.
Okay.
So it's a simple question. Will there be a German translation with the exam?
As with Mathematics 1, there will be a German translation aid with the exam. So no official translation, but let's say a best effort translation that should hopefully be enough for you to get the questions. The official questions will always be the English ones, though.
Thank you.
If there's any more questions about the exam, by the way, I'll be happy to answer those, but please postpone this until the end of today's exercise session, so we don't get distracted from the important materials today. Okay, so let's enter the poll right now, and I'll publish the results for you. So volume computations seem to be troublesome, and polar coordinates don't seem to be that easy either. So we have some examples of those on today's central exercise session. We'll talk about those. And integration over domains by vertices, I also have an example of those, so we'll also touch that, but I can try and keep that a little more brief then. Okay, let's start the screen sharing again. So you should hopefully be able to see my screen right now. And then I'd say let's start with today's problem session. So I just start with the first problem on the sheet as kind of a warm-up then. That is 11.8. And then I'm asking you to integrate a function over a triangle defined by the vertices. So we have the triangle that's called D, and that is defined by the vertices 0, 0, 2, 0, and 1, 3. And if you have something like this, it's probably a good idea to make a quick sketch to see how this thing actually looks like. So we do just that. So here's x1, here's x2, and let's try and sketch that. So we have the origin. That's 1 point here, 0, 0. We have 2, 0. That is approximately here. 2, 0. And then we have 1, 3. 1, 2, 3. So that is this point here. And that means the triangle that we're talking about is these 3 sides here. So we're integrating over this domain here. That is a set D. Okay, and I'm asking you to integrate a function over d. The function is x1 squared x2, dx1 x2. So what we have to do here is we have to find a description for d that is suitable for integration. D is not a box, obviously, so we cannot just use integration over boxes. But what we can do is we can use integration over normal domains. To do that, we need to have a description of that set D in terms of inequalities. So we'll start with that. There's basically 3 inequalities that determine this set here. So first one, this boundary line here, that is easy. That's just the inequality x2 is greater or equal to 0. Then we have those 2 other lines here, this one and sorry, this one. Let's start with that first here. So this is the line that passes through the origin and through the point 1, 0. That means the slope of that line is 3, and it passes through the origin. So what we get here is the equation x2 is equal to 3 x1. So that's the equation of this line. And if you want to have the interior of that triangle, then we need to turn this into an inequality. And basically, x2 is allowed to take on values on the line and below the line, not above the line. So that means the corresponding inequality would be x2 is less or equal to 3x1. And finally, there's this line here. And you can see this also has a slope of -3 in this case. Yeah, so the slope is the same but negative as with the other line. And it passes through the points 1, 3 and 2, 0. So the equation here is something like x2 equals minus 3x1 and now plus some constant. And to determine that constant, we can just use any point on the line, for example, 2, 0. And if we do that, it means we get a 2 here, get a 0 here, and then we can determine C. So if we substitute that, then we get 0 equals minus 6 plus C. So that means C has to equal 6, right? So we get minus 3x1 plus 6. And of course, in case you don't know the slope, you could just make a more general ansatz and then substitute the 2 points that you know on this line. Okay, so it doesn't really matter how you get to that description. Let's turn this into an inequality as well. So these are the points on the line. And again, the points that we're interested in are the ones below that line where x2 has a value that is less or equal to this, right? So x2 needs to be less or equal to minus 3x1 plus 6. Okay, so that's an inequality description of that triangle. And now we want to describe D as a normal domain. Normal domain, that means we have like a chain of inequalities where one of the variables is bounded only by 2 constants above and below. The next variable is then bounded by some expression in that first variable, only in that first variable, and possibly constants. The third variable would be bounded above and below by some expressions that only use the first 2 variables, and so on and so forth. So that if we just reverse that order and integrate that from the last variable up to the first one, then we eliminate variable by variable in that integration process until we have an integral where the boundaries are just constants. It basically doesn't matter how you order the variables, you just have to respect that order in the integral then. So we can either try and make x1 the constant bounds, or we can make x2 constant bounds here. In this example, it's probably easier to make the x2 bounds the constant ones, because if you have a look at this example from the x2 axis, you can see x2 is bound by 0 and by 3. Those are the two bounds for x2. Those are clearly constants. And then x1 is bound by a function in x2, like this, from below. And here's the upper bound, again, a simple function in x2. So that's probably the easiest way. You could also just reverse that. You could also say, well, x1 is bound by 0 on the left and by 2 on the right. Those are constants. And then x2 is bound by 0. That's easy. And by this function here, dependent only on x1. The downside of this approach is that this function doesn't have that nice of a description. It's still linear, but it's two pieces. So I would prefer the other approach here. But either way, you should reach the same result. Yeah, either way is fine. Okay, so we describe D as a normal domain. That means D consists of all points x1, x2 in the plane, where I said we start with x2, and we bound that by constants. So x2 is bounded, by the constants 0 from below and 3 from above. And then what about the x1 bounds? Well, we have these inequalities here, and here. We just have to reformulate those a little. So this here, we can solve that for x1, obviously. And that will give us x1 is greater or equal to 1/3 x2. And this here, we can also solve this for x1, and that will give us x1 is less or equal to, let's see, 1/3 minus 1/3 x2 plus 6/3, that's 2. Okay, and then we have our bounds for x2, for x1, sorry. So x1 is bounded below by this expression and above by this expression. So we get 1/3 x2 is less or equal to x1 is less or equal to minus 1/3 x2 plus 2. And that's a description of D as a normal domain. All right, so you can see the chain of variables here. The outer one, x2 in this case, that depends only on constants. x1 then depends only on expressions that depend on x2 and constants. And of course, you could go on if you had higher dimensions with x3, x4, and so on. Okay, now using that, we can solve the integral. So this integration, this can then be written as a successive integration. The outermost integral is the one with the constant bounds. So here we take x2 from 0 to 3. And then the inner integral is the 1/x1. So x1 varies between 1/3 x2 and minus 1/3 x2 plus 2. And we integrate the expression x1 squared x2, first with respect to x1, so dx1, then with respect to x2, so dx2. And now we just have to do the computations. Let's keep the outer integral, just copy that one. For the inner integral, we integrate this expression here with respect to x1. And then we get x1 to the third over 3 times x2. So that is x1 to the third over 3 times x2. And the boundaries 1/3 x2 and minus 1/3 x2 plus 2. Then let's substitute the boundaries. So again, we copy this integral sign once again. And then we have x2 times, so first bound here is 2 minus 1/3 x2 to the power of 3. Minus, and the lower bound, that is, sorry, I think I messed up with the third, right? Yes, right. So I forgot, I should take out the third. Okay, and the lower bound is then 1/3 x2. So we have 1/3 x2, again to the power of 3 dx2. That should be it, yeah. Okay, let's take out that 1/3 here. You can just move that in front of the integral. And then let's see if we can simplify this expression a little before we do the integration. We have this x2 here. And here we have this to the power of 3. So, well, basically we need to compute that. So what we get here is 2 to the power of 3 minus 3 times 2 to the power of 2 times 1/3 x2. Then we have plus 3, 2 to the power of 1 times 1/3 x2 to the power of 2. And finally, we get minus 1/3 x2 to the power of 3. So that is this first expression here. It's just a generalized binomial formula. And that last expression here, that is just 1/3 x2 to the power of 3 dx2. Okay, so let's see what we can simplify here, if we can simplify something. Let's copy the integral once again. So what do we get here? Only constant that appears in here is this 2 to the power of 3. Everything else is contains at least 1 x2. So we can't simplify anything there. That means we have 2 to the power of 3. That is 8 times x2. This is this x2 here. Then let's see, we have, well, basically there's not much that we can simplify, right? We have this x2 expression. There's no other x2 expression in here. So we can cancel out the 3, of course. So we are left with 2 to the power of 2. That's 4. So minus 4 x2. This one here. And then times this x2. So we get an x2 squared here. Next one is this expression here. There's an x2 squared, and we don't have another x2 squared. So what we have here is, again, the 3 will cancel out. One of the 3's will cancel out. We have 2 times 1/3 times x2 squared. So that's 2/3 x2 squared times x2. Again, this outer one here, that's x2 to the 3rd. And finally, we get this expression here. So that's minus 1/3 x2 to the 3rd minus 1/3 x2 to the 3rd, 2 times the same expression, at least that one. So we get minus 2 over 3 to the power of 3 x2 to the power of 3 times x2, this outer one again. So that's an x2 to the power of 4. Okay, a little long, but not actually complicated. So we can integrate that. And what do we get here? So we get x2 integrated is x2 squared over 2 times 8. That leaves us with 4x2 squared. minus x2 to the power of 2. If we integrate that, we get x2 to the power of 3 over 3 times 4. There's nothing that we can cancel out here, so this is minus 4 over 3, x2 to the third. Then we have 2/3 x2 to the power of 3. Integrating that yields x2 to the power of 4 over 4. So we can cancel the 2 and part of that 4. And that means we are left with 1 over 3 times 2. That would be 6. X2 to the power of 4. And finally, this last expression here, integrating x2 to the power of 4 yields x2 to the power of 5 over 5. And again, there's nothing that we could cancel here, so we get minus 2 over 3 to the power of 3 times 5, x2 to the power of 5. And we have boundaries 0 and 3. And finally, let's see how this works out. So upper bound 3, that means we get 4 times 3 squared minus 4/3 times 3 to the power of 3 plus 1 over 6, 3 to the power of 4 minus 2 over 3 to the power of 3 times 5 times 3 to the power of 5. And the lower bound, that's just 0. So we have 1 over 3rd. So that means we have 4 times 9. So that's 36, right? Then we cancel out 1, 3 here. So we have, again, 4 times 9. I shouldn't have computed that. Minus 36. So here we have 1, 3, and we can cancel out 1, 3 here. So that means we get plus 1 over 2 times 3 to the power of 3. So that's 27. And here we get, let's see, we have 3 to the power of 3 and 3 to the power of 5. So that leaves us with 3 to the power of 2 after canceling that out. So that's 2 over 5 times 9. Okay, and finally, if we do the computations here, let's take out the 1 over 2 and 1 over 5, so that's 1 over 10. We can again take in that 3, so we get 27 divided by 3, that's 9, and we get 9 times 2 divided by 3, that's 2 times 3. So all in all, we should get 33, if I'm not mistaken. So the result is 33 over 10, hopefully. Okay. Any questions about this one, Arda?
Yes. So one person asked whether you could show the second approach with choosing x1 as the independent variable.
Maybe let's postpone this and see if we have time at the end.
Okay.
Otherwise, I'll put it in the suggested solutions.
And
Maybe let's just catch it quickly. Anything else? Otherwise, maybe I just give a quick sketch of how this approach will work without actually going through the motions.
Also, one more question. Someone didn't get the point where you inserted the limits in the first integration, and I didn't quite get the question. But
we inserted the limits in the, so that happens here, right?
I'm guessing that, yes.
Okay, so yeah, basically there's not much to understand. What I'm doing is, maybe that was a little quick. I'm taking out this 1 over 3 here. and I'm also taking out this x2. Let me mark that again. So this is constant as far as x1 is concerned, so I'm taking out this constant before I insert the limits, right? So I'm only having x1 to the third left, and then the limit is this one. Yeah, so that's this limit to the third minus the lower limit, this one to the third. So maybe this taking out x2 over 3 was a little quick. Anything else?
No, you can just show the normal representation of the.
Yeah, so let me just show how you can represent D in a different way. Let me actually copy that here.
So the student also said you can just show it in the normal representation. No need to calculate it all.
Mm-hmm. Great. So I'll just show that, and the rest of the approach is pretty much the same. That's not that important. Okay. So what we can also do is we could describe this in terms of x1 being the first variable bounded by constants. And if you wanted to do that, the problem is the bound for x2. The bound for x2 is given by this function here, the upper bound. And basically that's a piecewise linear function. So we have to stitch together two linear functions to make that work. And probably the easiest way to represent this is to have our normal, to split up our normal domain. So what I do first is I cut that into two pieces. And I'll say the integration over this whole green area is the same as first integrating over the left half of the green area and then the right half. So this first left half, this is where x1 is between 0 and 1. So I'll take this one here. And then x2 is between 0 and 3x1, right? This is this function. And then I'll take the union of this set and the right half. Right half means I'm now in this area here. So x1 is between 1 and 2. And x2, sorry, there's a 2 missing here. x2 is again between 0. And now on the right side, we have this function as the upper bound. So that is the function x2 is less or equal to minus 3x1 plus 6. So that's the upper bound. And then I can just compute the integral over this part plus the integral over this part. Okay, I hope that clarifies the question. I'll add the computations to the suggested solutions, but they're not very different from what we just did.
Yeah, I think that satisfies the question. So,
good.
Yeah.
Anything else?
Oh, so one student asked whether we couldn't just compute 1/2 and then multiply it by 2. And
yeah, in this case, of course, no, you can't actually.
That's important. Yeah.
Sorry. So problem here is we're not computing the area of the triangle or something like this. We're computing a function over that triangle. You don't actually see the function in this image here. So you're right in saying that, of course, the domain is totally symmetric. And if the function has the same symmetry, then we could do that. But the function does not have that symmetry as far as I see it. Right? So the function values of the first half will be different to those of the second half. And that's why this approach doesn't work that easily.
So yeah, this was the question.
Okay,
Nothing
good.
more.
Okay, so I guess we'll just move on to the next one, C11.9. That one is about polar coordinates. So in 11.9, we have a disk of a radius 2 around the origin, so D. oh, sorry, D is given as all points x1, x2 in R2, where x1 squared plus x2 squared is less or equal to 4, which is 2 squared. So remember, you can describe a disk or a circle by the equation x1 squared plus x2 squared is radius squared. So if the right-hand side is 4, that means the radius is actually 2. And this is the domain that we want to integrate over. And we want to do this using polar coordinates because we are talking about a disk. So this is something that is easily described by polar coordinates, not so easily described by Cartesian coordinates. So what we do here is we use a transformation for polar coordinates that we have talked about in one of the earlier lessons in this semester. So just to remind you, let's make a quick sketch here. Polar coordinates. So what we're doing is we're describing a point in the Cartesian coordinate system, like this point here, by means of its radius. That means the distance of the point from the origin. So this is the radius, r, and by its angle. And that's always the angle between the x1 axis and the line connecting the point and the origin. So this is the angle phi. And this radius and the angle, those are the polar coordinates of the point. We can transform those into Cartesian coordinates by a transformation. We call that t here. And that works by simply taking r times the cosine of phi and r times the sine of phi. And that way you get the Cartesian coordinates that correspond to polar coordinates, radius r and angle phi. Okay, so this way we can describe the set D in a much easier fashion, as D is all t of r and phi, where, well, the radius is between 0 and 2, because we're talking about the whole disk, so not just the line, the whole disk. That means the radius is between 0 and 2. And we want to take the whole disk, so the angle there is between 0, that corresponds to this line, and then it moves around and around and around, and here we have an angle of 2 pi when we reach this line once again. So 0 is less or equal to phi is less or equal to 2 pi. And that means in polar coordinates, the description of this set of the circle is very easy. It actually looks like a polar box if you want, right? So the coordinates do not depend on each other. So it should be much easier to compute the integral using polar coordinates, and that is precisely what we are going to do. So if you want to integrate a function f of x1, x2, dx1, x2, using polar coordinates, then we can do this by simply using this transformation. So instead of x1, we substitute r times cosine of phi. And instead of x2, we substitute r times sine of phi. Like this. And then we have to also add a factor that somehow accounts for the change in volume that this transformation brings along. So that was the change of variables formula that we discussed in the lecture videos. What you need to do here is basically you need to determine the determinant of the Jacobian of that transformation, right? So doing that, and then multiplying with the absolute value of the determinant, that gives you the factor that you need here. And then you can just replace this integration by an integration over r and phi instead. You've seen in the lecture videos, in the examples, how to compute that determinant. And of course, the transformation between Cartesian and polar coordinates, that is always the same. So the Jacobian doesn't change. So the determinant of the Jacobian doesn't change. So that means this factor here doesn't change. That is always r for this specific transformation. Yeah, it might be different for other coordinate systems, but for the polar coordinates in the plane, this factor is always r. And you don't have to compute that. If it comes up on the exam, you can just know that or look it up. And by the way, that is something that should go into your cheat sheet. Okay, so let's do this substitution here. The function, this f, that looks somewhat complicated. That is square root of 2 minus x1 squared plus x2 squared to the power of 1 over 4. But you can probably already tell that this function will look a lot easier in polar coordinates, because this here is basically the norm of x squared. So that should be the radius squared. And if you do the computations, that's exactly what the result will be here. Okay, so let's do that substitution. What we get is, for the function f, square root of 2 minus r squared cosine squared phi plus r squared sine squared phi to the power of 1 over 4. So that's the function f. Times that r here, please don't forget that, dr phi. And now we're ready to just do the computations. Let's simplify this a little more. So what we get is square root of 2 times r. That's again this orange r here. Minus, and this one here, well, this is just r squared times cosine squared plus sine squared. And this here is 1. So we get r squared to the power of 1 over 4. And again, times this orange r, dr phi. Okay, so what we have is, once more this d here, square root of 2, square root of 2, that way around, times r, minus, and here we get r squared to the power of 1 over 4, so that is r to the power of 1 over 2, times r to the power of 1, so we get r to the power of 3 over 2 in total, dr phi. So now we can do the computations. It doesn't really matter which order we decide on, whether we first integrate with respect to phi or r, that doesn't make a difference. I'll just use phi for the outer integral. Phi goes from 0 to 2 pi. Then we have r for the inner integral. R goes from 0 to 2. And we need to integrate over square root of 2 times r minus r to the power of 3 over 2 dr d phi. So let's do the inner integration. So that is square root of 2 over 2 r squared minus, and this expression here, that will be r to the power of 5 over 2 times 2 over 5. So we divide by that new factor 5 over 2. Okay, and r varies between 0 and 2, and we integrate the result d phi. So outer integral again. Now the inner integral, what do we get here? That's the square root of 2 over 2 times, we start with this upper bound, times 2 squared. So that leaves us with 2 square root of 2 minus, and what do we get here? Let's see. I'll do that slowly rather. So that's 2 to the power of 5, and then the square root of that, power of 1 over 2, times 2 over 5. And the lower bound is just 0, so minus 0. Okay, so this whole thing is a constant that doesn't depend on phi in any way, so we can just take out that whole constant here. We get 2 square root of 2 minus, so the square root of 2 over 5, that is 2 to the power of 4, the square root of 2 to the power of 4 times 2. So we get 2 to the power of 2 times square root of 2 times 2 over 5. And then we have the integral from 0 to 2 pi over 1 d phi. And that is, of course, easy to compute. So that's 2 square root of 2 minus, we have 2 squared times 2, that's 8. So we have 8 over 5 square root of 2 here. And then this integral, that's just phi from 0 to 2 pi. So in the end, what we get is 2 pi minus 0. That's coming from this integration here. Times, and let's all put this on one fraction here. So we have 10 square root of 2 over 5 minus 8 square root of 2 over 5. So we are left with 2 square root of 2 over 5 then, and that means we have, together with this 2 pi, we have 4 pi square root of 2 over 5. Okay, and that's the final result here. Questions?
Just one question came up, and it is specifically for you. Could you once again clarify how is one supposed to integrate over an open set? And
Sorry, what kind of set?
open set.
An open set.
For example, if r is strictly greater than 0 and strictly smaller than 2,
okay,
how would the integral then look like?
Okay, so if we somehow exclude borders or parts of the borders, that does not make any difference for the integral. So those borders are basically, they're subdimensional, right? So if we are in dimension 2, then the border is a one-dimensional thing. And if you were to determine the measure of that, it would turn out that this has a measure of 0. So whether you include the borders in the integral or not does not make a difference. Same thing as in one-dimensional integration, right? So if you integrate over an interval, it doesn't really matter whether you include the boundaries or not. So you don't even explicitly mention that in the integral. And the same thing is true here. Whether you include the boundaries or not does not change the integral. So that doesn't really matter.
I guess that satisfied the question. And one more question.
Mm-hmm.
So where does the integral 1 d phi come from is the question.
This 1 d phi. Okay, what I did here is, let's mark that somewhere. So I took this expression here. I took that out of the integral because it doesn't depend on phi. So it's a constant, at least as phi is concerned. And then I'm left with basically with nothing. Or in a more elaborate way of writing nothing here is I could just say, oh, I'll multiply this by 1, and this is the 1 that is left here. Just so I don't have an empty integral. People also write empty integrals, of course, right? So you could also write this as integral from 0 to 2 pi d phi. It means the same thing.
So I think That should answer all the questions.
Great.
Yeah.
Good. So polar coordinates, coordinate transformation, change of variables is clear, hopefully.
Sorry, one question is whether you could clarify how you got the polar coordinates.
How I got the polar coordinates,
Yeah,
meaning the description of the set D,
I'm guessing yes.
I'm guessing. Okay, so D, as I said, D is a circle. So let's make a quick sketch here. Well, let me copy that actually. So I have a little more space. Let's just copy that over here. So that is the description of D. And if I were to make a sketch of that set, then, well, this condition basically means all points that have a distance of at most 4 to the origin, or distance squared of at most 4 to the origin. So a distance of 2 or less. And that is simply the circle around the origin of radius 2. So basically this is the set D. And now the question is, how do I describe that set in polar coordinates? Well, obviously the radius is limited. The radius is the distance of a point from the origin. So that is limited by this line here. The maximum radius I can get is 2. The minimum radius I can get is 0. So that will be between 0 and 2. And this whole set is totally symmetric. So it doesn't really matter. Just a second. So it doesn't really matter at which position I'm looking at that set, right? So if I rotate around here, again, the radius is somewhere between 0 and 2. It doesn't depend on the angle. And the same is true for the angle. If I look at the angle of a point in that set here, then anything between 0 would correspond to that line here, and 2 pi, the whole rotation here around here is allowed, right? So angle of pi over 2, for example, would correspond to that line. An angle of pi would correspond to that line. Here's 3 pi over 2, and so on. And all that works fine. Maybe let's do another example where we don't take the whole circle into account. So for example, if we had a set like this here, right? And let's say here's -2, here's 2, here's 2. And we just want that upper half, just as an example, just the upper half of that circle here. Then again, the radius would vary between 0 and 2, right? Independent of the angle, it's always the same for the radius. The angle, that would now vary between 0, which is here, and this other extreme here, that is pi. So this corresponds to an angle of 0. This corresponds to an angle of pi. Anything between is fine. Anything above pi is not, because that would get us into this area here, and we don't want to get here, right? So this example would be described by, by 0 less or equal to phi less or equal to pi. So basically your best guess is probably to make a quick sketch and then see how you have to vary r and phi in order for that to work. And of course, there could also be more elaborate areas where those might be connected. We'll probably see some examples in the exercises next week. Other questions?
One more question popped up. So the question is, how would this transformation look like for a more general circle, like an ellipse?
What you basically do is, well, you can do two things. You can either move the origin, of course. So we only had circles around the origin. You can certainly move that. That's the one generalization that you could do. And if you were to move the origin around, you would do something like, instead of just x1 squared, x2 squared, you would have an expression like x1 minus a plus x2 minus b, both squared, is less or equal to radius squared. So that's a circle that is centered at the point AB instead of the origin. And if you wanted an ellipse, then you would basically balance the contributions of x1 and x2 differently, right? So for example, you could do something like 2x1 squared plus x2 squared is less or equal to, let's just say 1 here. And that would mean x1 and x2 count differently in a way. So again, let's try and make a very quick sketch of that. Oops. So the easiest way is probably here to consider points where one of those coordinates is 0 and then see what the other can do in the limits. So for example, if x1 is 0, meaning we are somewhere on this axis here, then x2 can obviously vary between -1 and 1. Yeah, so as usual. So we would have -1 and 1. Now, as far as x1 is concerned, if x2 is 0, if we are on this line here, then what can x1 do? Well, it can vary between 0 and 1/2. With 1/2, we have, let me write that down. So if x1 is 1/2, we have an expression like 2 times 1/2 squared. That would then be 1. And of course, it can also take a value of -1/2, that's fine. But it can't exceed those, right? So when it goes beyond 1/2, then this 2 times x1 squared would be greater than 1. So the limits for x1 are 1/2 and -1/2. And that means we're roughly here, right? So it's -1/2, 1/2. So this here would describe an ellipse like that. Okay? And of course, then the relation between angle and radius is not that easy anymore. If you were to describe that in polar coordinates, that means the radius is now dependent on the radius, on the angle, or vice versa.
Okay, so yeah.
Does that answer the question? Good. Okay, so I'd say let's get to the last one. That is 1110. So the problem statement says, consider the curve given by x3 equals 1 minus x1 for x1 between 1 and 0. And then compute the volume of the three-dimensional body that arises by rotating this curve around the x3 axis. So let's have a look at how this is supposed to work. Oops. So let's say this here is the x1 axis, and this here is the x3 axis. So we're looking at the x1, x3 plane now. Now this function here, x3 equals 1 minus x1. How does that look like? Well, if x1 is 0, then this function is at the value 1. If x1 is 1, it is at 0. and it's just a straight line in between. It's an affine function after all. So there's a 1 here. And that function just looks like this, okay? So this is the function x3 equals 1 minus x1. And this is now rotated around the x3 axis, where the x1, x2 plane is the bottom of the body. So what happens here? Well, say you're rotating that line here around the x3 axis, then what you'll get is something that will look, well, to not just look like, it will be a cone, right? And you do the rotation, that means the basis of the cone will be a circle. And this line here, if you rotate that around the axis, that will form the surface of the cone. Okay, and the question is, compute the volume of that three-dimensional body. So how do we get the volume of that three-dimensional body? Well, basically, we have to describe that three-dimensional body and then integrate over that. So the question is, how do we describe that body and which coordinate system is best suited to that? And you can probably guess that cylindrical coordinates might be a good choice, because that rotation in the x1, x2 plane, that is aptly described by polar coordinates. And then we have this height component. And that's just what cylindrical coordinates do. They have polar coordinates in the x1, x2 plane, plus a height above that plane or below that plane. And that's our x3 coordinate. So the resulting body here, that B, can be described in cylindrical coordinates. So remember the transformation, it's on the sheet as well. So cylindrical coordinates means you have r and phi, right? Those two are the polar coordinates in the x1, x2 plane. And then you have a height component, an x3 component, basically. So the transformation from those into Cartesian coordinates works almost as with polar coordinates. You get r cosine phi, r sine phi for the first two, just like polar coordinates, and then you just add the height. This is basically exactly the Cartesian coordinate x3. Okay, so this is a transformation of cylindrical coordinates. And once we have that, we can describe this body B. And we can describe it as all points Tr phi h, where, well, the radius is this distance here, right? So we're rotating that line around the x3 axis as well. That's the radius of the base that we get. So that is between 0 and 1. Then we have the angle. We're rotating all the way around until we get a closed surface again. So that means we have to rotate between 0 and 2 pi. And the last one is the height. And that depends on the radius, as you can see here. So this height function here, if the radius is, for example, at this point, then this is the corresponding height. If the radius is here, and this is the corresponding height. If it's here, this is the corresponding height, and so on. So this is precisely this x3 function. Yeah, the height is described through this function of x1, and x1 corresponds to the radius here. Okay, so what we get for the height function is exactly that is between 0, of course, and 1 minus the radius. Right? As we move outwards from the origin, the height decreases until it hits the 0 here. And as you move inwards, it increases until it hits 1 here. So that's exactly how we can describe this B in cylindrical coordinates. And that means all we have to do is we have to compute the volume of B as the integral of the one function over B. And we want to do this using cylindrical coordinates. Let's first do x1, x2, x3 like this. We want to do this using cylindrical coordinates, so that means what we need is the determinant of the Jacobian of this transformation T. And I don't think we have discussed this anywhere yet, so let's quickly compute that. Just copy that function here. So we want to determine determinant of JT, sorry, of R phi H. Okay, well, how do we do that? We first compute the Jacobian, of course, JT of R phi H. So let's first do the derivative with respect to R. That is cosine phi, sine phi, and 0. Then with respect to phi, that is minus R sine phi, R cosine phi, and again 0. And then with respect to H, and that is 0, 0, 1. So you can see this has a pretty nice structure. Now we can easily compute the determinant of that one by just using Laplacian expansion, for example, with respect to that third row here. So we get 1 times minus 1, third row, third column, so 3 plus 3, times, and then we need the determinant of this here. And that is R times cosine squared phi plus R times sine squared phi. So what we get is, well, minus 1 to the 6 is just plus 1. Cosine squared plus sine squared is 1. We can take the R out, so all that's left is R. So this has the same determinant as polar coordinate transformation. It's not very surprising, because we do not actually change anything with respect to x3. Okay, so we are ready to compute the volume now. So the volume of B is the integral of 1 over B dx1, x2, x3. And that is equal to the integral of 1 times R. So this is the absolute value of the determinant of the Jacobian, dr phi h in cylindrical coordinates. And that means we just have to do this integration. R and phi are constants, so we can take any one of those as the outer two integrals. I just decided to put R on the outside, then phi, and then comes the height integral. That has to come inside of the R integral somewhere, because the boundaries for the height depend on R. Well, the upper bound depends on R. And so we integrate R dh d phi dr. Okay, so what happens here is R equals 0 to 1. This expression here, this R, is a constant as far as h is concerned, and it's a constant as far as phi is concerned. So we can move that all the way out here. And then we have this integral over phi. And let's compute this inner integral over h. That's simply h, boundaries from 0 to 1 minus r, d phi dr. Okay, so what we get is r from 0 to 1, r times integral phi from 0 to 2 pi, and this here is 1 minus r minus 0, d phi dr. Again, this expression is a constant as far as phi is concerned, so we can move that outside of that inner integral. And we get r times 1 minus r here. And now we compute the phi integral, that's just phi from 0 to 2 pi dr. So this expression here, that becomes r minus r squared. And this expression, if we evaluate that, we get a factor of 2 pi minus 0 dr. Okay, so what that means is we can take this factor of 2 pi out of the integral, and then we integrate this expression with respect to r, and that gives us r squared over 2 minus r to the third over 3, r from 0 to 1. So we get 2 pi and then 1 over 2 minus 1 over 3 minus 0. Okay, 1 over 2 minus 1 over 3, that is 3 over 6 minus 2 over 6. So that leaves us with 1 over 6. Or altogether pi over 3. So that is the volume that we were looking for. Okay, any questions?
We just have one question. So the question was, how come we can't just set h to be bounded by 1 from above, given we know what values the radius can take?
Well, the problem is that the radius and the height depend on each other. So we have this function as the dependence. So we can either say we let the radius vary between 0 and 1, and then determine the height as a function of the radius, like we did. Or we could also say, well, let's let the height vary between 0 and 1, and then the radius is a function of the height. Yeah, we could also do it this way. Doesn't really change anything. But somewhere this dependence has to be modeled into the set. Yeah, otherwise, if everything, both radius and height vary between 0 and 1 independently, then what we would get here is, let's make a quick sketch here. What we get here is the body determined by rotating this area here, right? So here, the height and the radius are independent of each other. So we would get the full cylinder, basically, not just the cone. Let's remove that. Yeah. Other questions?
One more question. Is there a connection between the one-dimensional substitution rule and the multivariate case? And where does the determinant of the Jacobian come from, is the question.
Actually, the one-dimensional substitution rule is a special case of that change of variables formula. And if you just apply that change of variables formula to a one-dimensional integral, you will find exactly that. You will hopefully remember that the derivative of the substitution function enters the expression in the one-dimensional substitution rule, and that is precisely what corresponds to the Jacobian. Just try it. Take any example, one-dimensional substitution rule, and try to apply that whole machinery to that. And you will find if you actually do the Jacobian, you will end up with the derivative. And if you take the determinant of a derivative that is one-dimensional, then you will end up with the same derivative. So the formula that will pop out is exactly the one-dimensional substitution rule.
So, yeah, that was a good question.
Yeah, clever question.
Oh, so are we almost finished? Because there are some off-topic questions.
So if there's no more on-topic questions, yeah, I'll be happy to take off-topic questions then. I'm guessing exams is the topic.
So actually, I think there were no questions on the exam.
No questions on the exam. Wow.
Just one unrelated question is that how many problem sheets there will be? So
yeah, let me quickly talk about that. Today is the 6th. That means we are currently in week 12, I think, right? Yeah. So next week is week 13. There will be more videos in week 13, so we'll still learn something new then. The last week of the semester is the week after that. That's week 14, and there will be no more normal lecture videos in week 14, so we won't cover anything new beyond that. That means you still have a chance to practice all the materials that we cover until the end of week 13 in the last week of the semester. There'll still be a normal central exercise session. There'll still be tutorials. I'm planning to do a walkthrough of the 2 former exams that I published instead of the normal lecture videos in week 14, so that I'll demonstrate how to come up with the solutions here. And I haven't quite decided on what else to do. So if there's any suggestions, feel free to post to the chat if there's anything you want me to do in the last week. There will probably not be a dedicated exercise sheet for week 14 anymore. So 13 is probably going to be the last one.
Okay, so people have actually started asking questions now.
No, I shouldn't have said that.
So one question is, could you explain the process with the hash code during the submission of the exam?
Hash code during submission of the exam. So basically what happens is once you press the upload button in this TUM exam interface, your browser scans through your upload and computes a hash code, a fingerprint, so to speak, that uniquely identifies your submission. That's just a bunch of numbers. I don't know how long exactly, maybe 60 numbers or so in a row. And that is then uploaded to the server. That's a very small file, so that upload is very quick. Of course, your submission cannot be reconstructed from that, but it can be identified. So if the TUM exam server later gets the actual PDF upload, then it will compute this fingerprint once again using the same algorithm, and it will compare that to the fingerprint that you have uploaded before. If those are identical, your submission will be accepted. If they aren't, it will be rejected. So if you somehow manage to modify your submission after you've already started the upload, then this will not be accepted anymore. If for whatever reason your internet breaks down after you have submitted the fingerprint, the hash code, and before you did the actual upload of your PDF, then this is not a problem. You just start again. You just upload or press upload once more. The server will not accept the new hash code once the upload window is over, but it will accept the PDF, and it will try to compute the fingerprint of the PDF once it has received that and compare that to the hash code it has stored already. If those agree, and they will agree if and only if you did not change anything, then your upload is still being accepted. And this grace period will probably be an hour or 2 after the actual upload end, right? So you have to initiate the upload in time But if it completes after that deadline, then that's completely fine, as long as you don't modify the file in between.
And the same student also asked whether he would need to do anything after they upload their answers.
So once you press the upload button, you just wait until the browser says upload has been completed. Basically what happens is either the upload will be processed right away, or if lots of people press upload at the same time, then you get a waiting ticket. So you'll be assigned a number in the queue, and your browser will tell you you are number 17 on the queue, and then this number will decrease until the upload actually starts. And once that has been completed and you get a message, then you can close the browser and shut off your computer. Yeah, just wait until your browser tells you the upload has been completed. That hash code thing happens in the background completely automatically. You don't have to care about that.
One question, one more about exercise sheets.
Yeah.
Will there be a recap exercise sheet just like we had in Mathematics 1?
I don't know yet. Maybe not. That depends a little. Basically, what I'm usually do is I design the exam and retake at the same time, and then I have a few, let's say, leftover problems that didn't make it in the exams, and those might then be used for a recap exercise sheet. I'm just not quite sure if I can design the exam in time to have those leftovers ready.
Okay, one more question about the exam. Is the additional time to print and scan set now?
Is that what, sorry?
Is it set? Is it, so do we know?
I haven't taken a final decision. I'm guessing it will do 15 minutes. So from all the trial runs that I've seen so far, 15 minutes sounds reasonable. But there'll be a few more trial runs with other exercises, and if they come up with a completely different number, then I might change that. But for the time being, I say 15 minutes sounds reasonable.
And are people allowed to Google during the exam?
To what?
To Google.
It's open book, so if you consider Google a book, then yes.
So someone said, really don't know what we have to expect because of open book closure. That's not a question, but I'm guessing they're asking what.
They're asking what to expect. Yeah, I would like to know that myself. I haven't made the exam yet, as you can probably guess. So I still haven't quite decided, but I'm guessing something similar to the exercise sheets. I mean, that's what we practice, so I'm going to lean on that side. I'm not doing something completely different for the exam.
Oh, so one more question about the additional time. So do people only get the additional time if they actually upload a scan of the exam?
I have no means of checking if someone uploaded a scan or an electronic version, other than maybe looking at it and making a judgment call. So it doesn't matter what method you use. You'll get the 15 minutes no matter what.
Mm-hmm.
You also need some time to transfer your electronic version back to the computer or to the upload portal, and of course transfer your download to your iPad or whatever you have here. So it seems reasonable to give you a little extra time as well. And of course things might go wrong in that process, so you might need a few minutes to repeat or get a USB drive or whatever. So yeah, everybody gets those extra time, those extra 15 minutes.
Yeah, so I think that was all the questions.
Okay, great. Maybe one more note on the exam. For those who have not read my rant on the chat yet, please do not use the OneNote app. Under no circumstances will I accept OneNote uploads. So the ones who use that ended up with one long, very long page that contained the whole of the exam. And there's no way I can split this up into single pages afterwards. So it is important that you submit in your exam copy that the original pages are kept that way. So it's one original page per page that you submit. And even the OneNote app on Windows seems to move those pages strangely. So basically, whatever app you use must not tamper with the page layout in any way. Otherwise, we cannot accept these pages. I'll give you a few more details before the exam. And you've probably read through the term exam manual with suggestions for apps you might want to use. But that's the one thing I would like to note now. Please do not use OneNote. If you're used to that, please get some alternative.
So,
okay, that's it.
One question. Oh, two questions. So which one is the best one in your opinion?
Sorry?
So a question about, I think, the digital writing apps for iPad or for tablets. Which one is the best one in your opinion is a question.
So there are several choices here, and of course it depends a lot on the tablet and the system you are using. I can tell you I'm using GoodNotes for these exercises and for pretty much everything I do, and that works fine. I've tried that with the term exam system, but there's other apps out there that also work great.
Yeah. Well, one question also said whether you could recommend some scanning apps for phones.
Some scanning apps for phones. So I only have experience with the with Apple phones, iPhones, and they have an integrated scanning app. The Files app has a scanning app that seems to work good. I haven't tried that myself, but that's the recommendation of the term exam team, and they have tried that. That seems to work fine. Of course, the same should be available on the iPad. I've tried that actually, that works. But if you have an iPad, there's probably no need to scan anyway. I don't have any experience with Android, but again, there are recommendations in the term exam manual. The one app they warn against is Cam Scanner. That seems to somehow mess up the scanning input. So it seems to apply some optimization mechanism that makes the QR codes basically unreadable. So please don't use that. Otherwise, I can't recommend anything. Have a look at the manual. There are recommendations in there.
So one question.
Yeah.
Where do you find the exam manual is the question.
It's on Moodle. I uploaded that on Moodle. Hopefully.
Yeah.
I'll check. Yeah. If I didn't upload that on Moodle, I will do that now.
And I think that's all the questions. Yeah, I think
okay.
That's
good.
All.
Great. So thanks a lot for attending. Thanks a lot, Arda, for moderating the chat. And I'll see you all on Thursday in the tutorials, hopefully. I'm sure I'll see you, Arda.
Yeah.
So thanks and see you then. Bye.
Everyone. Bye.